Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon. Ever find yourself lost in the ticking hands of time, wondering whether our understanding is only a small portion of the temporal iceberg? On its head, his revelation is not just a theory. It's a key that could unlock the doors to the universe's mysteries, revealing a universe more intricate and inspiring than we ever dared to imagine. How does the brand new theory of Brian Cox challenge our traditional understanding of time? And what are the potential implications for our perception of reality? Join us on an intriguing exploration through the annals of time itself as we delve into Brian Cox's groundbreaking theory, recently revealed, on the nature of time in the vast universe around us. Mysteries are waiting to be uncovered, and some of these mysteries involve puzzling things about time and gravity, essential parts of our existence. Imagine a world where time acts strangely. It can either slow down or speed up. Also, the force that keeps us on the ground might not be what it seems. This is the realm of relativity, with theories proposed by Albert Einstein, where our understanding of time and gravity takes a peculiar turn. Einstein, a well-known figure, provided us with a new way of looking at the universe through his theories of relativity. His work laid the foundation for understanding how time behaves in different situations, especially when traveling at very high speeds. It all began at the start of the 20th century when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. Simply put, it demonstrates that the laws of physics remain the same for all observers who aren't accelerating, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One fascinating thought experiment used to explain time dilation is the image of a light clock. Imagine being inside a spaceship moving incredibly fast, almost at the speed of light. Inside the spaceship, there's a beam of light bouncing between two mirrors, perpendicular to the direction of movement. According to the laws of physics, the speed of light is constant for all observers. So, the light beam must appear to travel along a longer diagonal path. The time it takes for the light beam to travel its path should be identical for both the observer inside the spaceship and the one outside. However, since the path appears longer for the outside observer, it seems that it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. In this scenario, time behaves differently depending on motion. Understanding how things change when they move fast, known as relativistic effects, is not just a theoretical idea. Scientists use big machines called particle accelerators like the Large Hadron Collider to make particles move super fast, nearly at the speed of light. When things move this fast, we must think about time in a unique way for accurate predictions and measurements. Albert Einstein introduced the special theory of relativity in 1905, which altered the way we see the universe, especially regarding change in time. This theory challenges our natural intuition. It states that the rules of physics are the same for everyone, regardless of their motion. This differs from our everyday experience, where we assume that if something is already moving and we add more speed, it simply gets faster. However, according to Einstein's theory, there is a maximum speed. Nothing can go faster than the speed of light. One fascinating consequence of this theory is that events that seem to happen simultaneously for one observer might not appear that way to another moving at high speed. Another surprising idea is length contraction. This means that if something is moving, it appears shorter in the direction of its movement when viewed from a stationary frame of reference. Then there's the well-known equation E equals mc squared, which shows that energy and mass can transform into each other. This is crucial for understanding how tiny particles behave when moving at high speeds and for phenomena like nuclear reactions. In the real world, special relativity isn't just a fancy theory. It's something we use daily. Technologies like GPS depend on it. When GPS satellites send signals to your device, they are moving, and because of this motion, time behaves slightly differently for them. If we didn't account for time dilation in GPS calculations, navigation systems would be significantly inaccurate. So, special relativity teaches us that time isn't the same for everyone. It all depends on how things are moving. This challenges our usual understanding of time and space. It's like realizing that our normal perception of the universe is a bit off. According to the special theory of relativity, time isn't fixed. It changes with movement. Some fundamental ideas, like the speed of light always staying the same and the relationship between energy and mass, have been proven through numerous experiments. But there's more. Enter Einstein's general theory of relativity, proposed in 1915. This theory delves deeper into the relationship between gravity and the structure of the universe. It shakes up the old idea that gravity is simply a force that pulls objects together. Instead, it reveals that gravity occurs because space and time are curved. Rather than being some mysterious force, gravity is simply the natural movement of objects through curved spacetime. Imagine spacetime as a massive, stretchy blanket. When something heavy like Earth is placed on it, it creates a dent. If you place a smaller object like a ball near the Earth, it will roll toward the dent. This is similar to how gravity works, not as an invisible pulling force, but as an effect of curved spacetime. General relativity provides an explanation for how planets orbit the Sun, accurately predicting their paths. It even explains why Earth follows an elliptical orbit rather than a perfect circle. This is different from the old idea of gravity merely pulling things together, which struggled to fully explain planetary motion. Instead, Einstein's theory suggests that space and time are like a flexible fabric, bending under the influence of massive objects. This concept was confirmed by a crucial experiment during a solar eclipse in 1919, when Sir Arthur Eddington commanded a group to investigate how distant starlight bent as it passed close to the Sun. The theory states that the mass of the Sun would alter the shape of the starlight slightly during an eclipse. Einstein's observations were consistent with predictions, establishing the validity of the theory. Just as motion can change how we experience time according to special relativity, gravity also impacts time. In locations where gravity is particularly strong, time slows down compared to areas with weaker gravity. So, if you were standing close to a massive object such as a black hole, a clock would move at a slower rate than one placed far from this massive mass. General relativity introduces the idea of black holes, which are places where gravity is super intense. Inside a black hole, the force of gravity is so powerful that not even light can escape from it. The edge surrounding a black hole is called the event horizon, and it seems like there is no going back. Once something crosses this boundary, it gets pulled into the black hole without any chance of returning. Einstein's theory of general relativity has important implications for the nature of the universe. Initially, he added something called a cosmological constant to his equations because he thought the universe was static. However, when it was discovered that the universe is expanding, he referred to this as a big mistake. The idea of an expanding universe, based on general relativity, is a key part of the Big Bang theory, which describes how the universe began. Another important concept from general relativity is gravitational waves. These are waves etched into the fabric of space and time as a result of extremely massive objects moving rapidly, such as when neutron stars or black holes merge. In 2015, researchers at the Laser Interferometer Gravitational Wave Observatory, LIGO, directly detected gravitational waves, providing proof for another aspect of Einstein's theory. Over time, scientists have conducted numerous tests to determine whether relativity is true, and each time it has proven to be correct. Whether by observing the bending of light from stars as planets move or recognizing gravitational waves, general relativity remains a robust and reliable theory. Claiming that gravity is false is difficult, especially considering that we experience gravity every day. In physics, discussing and exploring different ideas is commonplace. Scientists like Brian often question established theories, and some challenge the conventional way we think about this fundamental force. One idea that challenges traditional gravity is called modified Newtonian dynamics, MOND, which suggests that gravity behaves differently at slower speeds, particularly in galaxies, without the need for dark matter. Rather than requiring more invisible matter, MOND proposes that gravity strengthens at low speeds. The gravity debate also involves obscure notions of dark matter, and the introduction of dark energy to explain certain phenomena in space. Critics argue that these concepts aren't necessary and that alternative theories can explain what we observe. Some scientists who disagree with Einstein's gravity theory explore new options, such as theories involving unknown particles or forces that could modify or enhance our understanding of gravity. It's important to emphasize that new concepts in science aren't ignored. Rather, they are rigorously tested to see if they make sense. For example, Einstein's notion of time in four-dimensional space, where time travel may be constrained by the speed of light, has been creatively explored. Concepts like shortcuts and wormholes have been considered by scientists such as Stephen Hawking, whose chronology protection conjecture suggests that time travel is unlikely from a physics perspective. Ongoing experiments and observations seek to determine whether these new theories can explain phenomena like gravity in a manner consistent with what we already know. While various ideas have been discussed, none have convincingly replaced the well-known theory of general relativity. Doubting the rules of gravity and challenging established ideas are vital aspects of scientific development, leading to additional research and a deeper understanding of the universe. In general, theories about gravity continue to evolve, but relativity remains the most significant one. Despite difficulties and alternative ideas, it consistently performs well in tests and explains various phenomena, such as planetary motion and the bending of light around massive objects. General relativity remains strong because it is simple and encompasses a wide range of phenomena. As previously discussed, Einstein's special theory of relativity states that time can behave differently depending on motion. Now, let's explore how this idea affects real-life scenarios, especially in space travel. Space travel is exciting but challenging because space is vast. Additionally, according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a significant challenge, even with advanced technology, due to the lengthy time required to reach the nearest stars. Think about the well-known twin paradox to understand what happens with time when traveling in space. Picture this. One twin stays on Earth while the other twin goes on a fast trip to a distant star. When the twin who travels through space returns, they find that less time has passed for them than for their twin on Earth. This indicates that they have effectively traveled into the future. Time is crucial for space travelers because the longer the journey, the more time slows down. If astronauts were to visit nearby stars, time would significantly slow for them, and they might age more slowly than people on Earth. While this may sound like science fiction, it is a real consequence of relativity theory. Imagine if humans send a crew to a star system not too far away. Due to the immense distance, the trip could take many years. Even if they traveled at high speeds, the time spent by the astronauts would feel shorter due to the time dilation effect. However, on Earth there would be a noticeable time delay. This effect impacts not only living beings but also communication and computer technology. Devices on spacecraft must account for time dilation to function accurately at high speeds. Space travel also presents physical challenges, such as prolonged isolation, exposure to cosmic radiation, and the psychological consequences of being away from Earth for extended periods. For our daily lives, we can observe the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it is crucial to factor in these effects for accurate GPS calculations. Failing to do so would have a significant impact on the precision of navigation systems. Now let's explore why time moves in one direction. Time governs our lives and the universe, flowing from the past to the present and future. This one-way passage of time is essential to our existence. But why does time have this one-way nature? To understand this, we look at entropy, a concept that measures disorder or randomness in a system. Entropy is linked to the arrow of time, as it tends to increase over time, causing time to flow in one direction. The second law of thermodynamics states that in any isolated system, total entropy will either increase or, at best, remain constant. In simple terms, entropy,